Hermite says, I believe the numbers and functions of analysis are not the arbitrary results of our mind, but they exist in an objective reality and with the same character and necessity as things of objective reality. We meet them and discover them and study them as the physicists, chemists, and sociologists. Analysis in this quote refers to mathematical analysis, which is the study of functions and vector spaces. Well, it relates to you guys because many of you are studying calculus, which is the beginning of mathematical analysis. And I think learning more about mathematical analysis will help you to gain a different perspective on calculus and have better understanding of its nature. Well, I'm interested in the theory of mathematical analysis because I'm a math major and I've been struggling with it for some while. And so I'll discuss first the two branches of mathematical analysis, then the history of it, and then the applications. Well, first, mathematical analysis has two major branches: real analysis and complex analysis. Real analysis is the study of functions of real variables. It involves the study of series, limit, continuity, and differentiation, integration. Well, differentiation is just, you take the quotient between the difference in y, which is the function, and the difference between x. So it's dy over dx, which is defined as differentiation as you take the distance small enough. And integration is basically you calculate the graph of the area under this function, this way. And the study of complex analysis is the study of functions of complex variables. Easy. And the important thing is that it introduces the concept of analytic functions. There you go. Analytic function is a function that is a convergent power series, and that's a power series. Examples include the gamma function, Riemann zeta function. And now you may ask me, why are they important? Why do we need these things? Now, let me ask you something. I think most of you guys know the volume of a sphere. It's 4/3 I times r to the cube. We know that, right? Yeah. And now if I ask you, what's the volume of a 4-dimensional sphere? What about a 5-dimensional sphere? What about an n-dimensional sphere? The gamma function gives a good generalization of the n-dimensional volume of the volume of n-dimensional sphere. Sorry. So that's the gamma function, and here's the generalization right here. It looks complicated, but n-dimensional sphere, isn't it cool?
Simple.
Right. And now we'll move to the history of mathematical analysis. It all started with Newton and Leibniz. We all know them. They developed the theory of calculus, the infinitesimal calculus, with derivatives and integrals in the late 17th century. Sorry. It is until the early 18th century that the formal definition of limit and continuity are developed. These are the important concepts. Because before this time, if someone asked mathematicians, what do you mean by if some random guy asks a mathematician how to do integrals or derivatives, they just say, take these difference small enough, infinitely small. If they're asked, what do you mean by infinitely small? And mathematician will only say, it's infinitely small, isn't that apparent? And they don't have an answer for it. So in the early 18th century, Augustin Louis Cauchy, this is one single person, he developed the formal definition of limit, which is the following, the Upsilon delta definition of limit. It basically means that if you line up all your numbers and it has a target, and you take the target close enough to that, take numbers close enough to the target, the difference between the target and the number will be arbitrarily small than a positive number of your choice. So that's, yeah. And In 1816, Bernard Bolzano gave the formal definition of continuity. Continuity basically means the function is smooth enough. So if you that's the definition. Well, in human language, that means if you work on a function, get close enough to a point, you actually get to the point on the function. You don't, the function is not, that point is not in some outer space. That's what it means. But it's important, It's important. And in the mid-19th century, Bernard Riemann developed the theory of integration with concept of limit and integration, rigorously. And with modern, the modern theory of real analysis was developed by Henry Lebesgue and Camille Jordan. The measure theory. It basically takes a set of arbitrary objects and assign it a number to it. That's the size of it, like your weight. And you may ask, why is that important? Like, we're good enough with what we had before, like with calculus, but why is that? It's important because now if you look at functions that can be integrated, meaning they can take you can calculate the area of the function. Like, when will it be discontinuous? Discontinuous. Like, when you can't take the integral of this function. Mathematicians try several methods to find a way to make this function not integrable. They take out like a point from the function, and they discover that it still can be integrated because you can just take a separate integral, take the two areas on two sides. And one thing mathematicians love is abuse their functions. Like, they would just take many points off their function and see if it still can be integrated. Well, it turned out they still can. And Lebesgue gives a very useful criterion to test whether a function can be integrated or not. It's the following from Tom Apostol's book, Mathematical Analysis, page 171. Basically means that if a function can be only integrated or integrable if and only if that this set K, the domain, has measure 0, meaning that it's small enough, like the size of it is 0. That gives like a really good criterion for Riemann integrability, meaning that if this function can be integrated or not. It's just a test. So the history of complex analysis is developed at the same time by basically the same set of mathematicians like Euler and Cauchy and Riemann, these people, all of them. Now we'll move to the history of mathematical analysis. Here's a quote from David Hilbert: "Physics has become too difficult for physicists." Okay. David Hilbert is the guy who helped Albert Einstein to develop his theory. Because Albert Einstein struggled 8 years to finalize his theory of gravity, and he came into David Hilbert, and David Hilbert provided him a mathematical model for his theory. So David Hilbert uses theorems for mathematical analysis to help Einstein, and he also helps to finalize the theories of other branches of physics, like string theory, quantum mechanics. And this is a book written by David Hilbert. It's called Methods of Mathematical Physics. It introduced the concepts of mathematical analysis and partial differential equations to help to cope with the problems in physics, the advanced theories. So it's really useful in physics as well as engineering and the theory of probability. Like, most of the advanced probability theory was based on the modern real analysis theory. So yeah, now you have a better understanding of the branches, the history, and the applications of mathematical analysis. I think you have a better understanding of the subject. Now, if you look at, like, whenever you go to your calculus class, don't think of it as a torture, but think of it as something that saves physicists' lives from depression and suicide. Because without mathematical analysis, without calculus, you just can't develop the theory.